Hey guys, we're going to talk about proofs a little more formally and really get to the heart of what we mean when we talk about performing a geometric proof. And to kind of get us started, I want to make sure we understand all proofs are is using what we call deductive reasoning. And this is a form of reasoning based on what we call it top-down logic sometimes, where we are using statements where the premise is met, therefore we can conclude some fact based on that premise being met, and basically stringing these arguments along. I know that sounds very out there and very abstract, but it's something we use every single day, and the most basic argument that we use is something called the law of detachment. Okay, so basically this is this idea that if P is true, then Q must be true, right? If I have a statement like that, we use these statements all the time, whether it's if you give me $1, I'll pay you back tomorrow, or it could be something like all dogs are animals. That is equivalent to saying that if something is a dog, then it is an animal. So we use these statements all the time, and we use this law of detachment all the time as well, because what it says is if you have a statement like this, and P is met, that hypothesis is met, then we know that Q must then follow, right? So if I make the statement, if you loan me $1, I'll pay you back tomorrow, then it is understood that as soon as I give you that $1, you're going to pay me back. That must be the conclusion that follows if that was a true statement. So, in math, here's an example. If I say that all four-sided polygons are quadrilaterals, right, and if I know that a square has four sides, then the only possible conclusion that we can draw is that a square is, in fact, a quadrilateral. There's no other way. There's no way this statement could be true and this not be true, because this part of the statement is met. That premise is met. So hopefully this is something you've been exposed to before, but it is a really important concept. The next one is something called the law of syllogism, which also can be likened to the transitive property. This is also something we use all the time, and we see it all the time. If you've watched any of the DirecTV commercials, they say it all the time, right? If you subscribe to cable, then your cable goes out, and you've seen all those ridiculous commercials, and you end up getting beaten by a gorilla or something like that. The concept is, if I have some sort of statement, like if P is true, then Q is true, and if I have another statement that says if Q is true, then R is true, then as soon as I know, hey, P is in fact true, I have an example of P, right? Then not only do we know Q is true, but the fact that Q is leads us to know that R is, so I can go straight from the fact that P being true means the only possible conclusion is that R is also true. Okay? So it's just an idea of stringing multiple lines of argument together. And this is something we do every day in our day-to-day life. It's how we reach conclusions all the time. Okay, so here's an example of one that's not mathematical. If Joe is sick, then he will be absent. If Joe is absent, then he will fall behind. So this must be true that if Joe is sick, the only possible conclusion is that he'll be absent, based on the statement, of course. If he is absent, which he is, we just because he's sick, we know he's absent, so now we know he's absent, which means he must fall behind. That's the only possible conclusion that can come from the idea of this premise of Joe being sick being met, right? That's the only thing that could possibly happen. And so what we have to realize when we're doing a geometric proof is that this is all we're doing. We're just taking one statement, which we know to be true, drawing some conclusion about what that must mean, and then making a new statement, right? So the only difference is it's not going to be about Joe being sick or about my cable being out or whatever else. They're going to be statements about geometric figures. So the big key, though, that I want to really stress, okay, the only thing that makes this a little bit harder is I'm not just stringing together a bunch of statements. I'm not just saying, well, let's go back to the coordinate proofs we've been talking about. I'm not just going to say, oh, well, since these lines are parallel, I know this is a parallelogram. We have to state why we know the lines are parallel. I must justify every single statement. Okay? We don't like what we call sometimes in math is a naked answer, right? I want to make sure any claim that I make is justified. Okay, what do I mean by this? You can even look at what I've written here. This got you a lot on the proof quiz we took. If I want to say line A is perpendicular to line B, I don't just say that. I say line A is perpendicular to line B because of something we know, right? And that may be because I told you that was true in the beginning. It may be because I found out that slopes were opposite reciprocal. It may be for some other thing we end up learning. But every time I make a statement, I have to justify. I have to say because or since or whatever. I have to give a reason that whatever I'm claiming is true and it must be true. So let's take a look at a proof. I asked you to think about this in class. We want to prove that the vertical angles congruence theorem holds. In other words, I want to prove that if I have two lines that intersect, that their vertical angles must be congruent. Okay? So the first thing I want to make sure I do is use things that we've already accepted as true, a very basic statements, and then I want to make sure that I know what does it mean for angles to be congruent. If two angles are congruent, what does that mean? Well, it means that they have the same measure. So I need to show that these two angles have the same measure. So I may start by saying, I know I want to link together the fact that 1 and 2 form a line, right? I know that the measure, well, let me say it this way. I know that angle 1 and angle 2 form line K because it was given to us. We know, that's line M. And I know that line M is a line, basically, because of given information. Okay? And so what we know is that if two angles form a line, what must be true? Right? We know that they form what's called a straight angle, which means they form a linear pair. Okay? So really what I could have said here is if angle 1 and angle 2 are a linear pair, which we just said above, then we know that the measure of angle 1 plus the measure of angle 2 must equal 180 degrees. We know this is true because we talked about this in class, that linear pairs always add up to 180. Now what I also can say and notice is that not only do 1 and 2 form a line, but 2 and 3 also form a line, right? So I can say angle 2 and angle 3 form line K, meaning they are a linear pair. Okay, if they're a pair of angles that makes a line, they're called a linear pair. This means that the measure of angle 2 plus the measure of angle 3 equals 180 degrees. Right? And so we do need to justify these statements, right? Here's a great example of making a statement and not justifying it. How do I know that this and this is true? Well, I know because right? Because of something called the linear pair postulate. So we can make this go a little smoother, but I would say this is true. These are both true because of the linear pair postulate, which is on the sheet of notes that I gave you, and is something we should know from the past. So we know these two are both supplementary. They both add up to 180. And so here's a great thing that hopefully we can notice. If 2 and 3 add up to 180 and 1 and 2 add up to 180, that means they must be equal. And I want to make a quick analogy. If I said that me and Joe combined have $100, and me and Jim combined have $100, then what does that mean about Jim and Joe? They must have the same amount of money because they're both adding it to my amount and equaling the same thing, right? So this means that if 1 and 2 equal 180 and 2 and 3 equal 180, since they both include angle 2, there's only one thing we can conclude, and that is that 1 and 3 are the same. And we can do this a little bit more formally with some algebra, right? I can say maybe that measure of angle 1 plus the measure of angle 2 must be equal to measure of angle 2 plus measure of angle 3. I know that these two statements come together to form this one because of what we call substitution. Right? I just took this and plugged it in where the 180 went to show that they're the same. And then you can kind of see how these would cancel out. By subtraction, we can say that these would cancel. By subtraction, the measure of angle 1 equals measure of angle 3, and therefore, hopefully you see we've gotten to where we want, right? Therefore, I know that these two angles have the same measure, which by definition, that's what it means to be congruent, right? What are two congruent angles? They're angles that have the same measure. So by definition, angle 1 is congruent to angle 3, and I can do my tombstone, and I am done. So this is just one quick example, and this is something we're going to become great at in the next coming weeks.